This is the second of the talks sponsored by RDS. A few years ago, I was at a conference and taking questions at the end, and I don't usually get hostile questions except from religious people, and they're extremely easy to handle. But then I got a hostile question which was not so easy to handle. It was a very tricky and a difficult question, and I thought, who is this? It turned out to be one of those I'm an atheist but questions, which are always the most difficult to deal with. It was, of course, Lawrence Krauss. I didn't take very kindly to it at the time. We've since become the firmest of friends, and I have enormous respect for what he's doing in the field of public understanding of science, which is the field that I recently retired from professing. He is, of course, a most distinguished physicist, author of many books. He also interests himself in science generally and in the promotion of the understanding of science generally. He's recently moved to Arizona to start what I think is an extremely exciting initiative. He is Associate Director of the Beyond Center and Co-Director of the Cosmology Initiative and Director of the New Origins Initiative at Arizona State University. So the study of origins of all kinds, right across the board, from the origin of the universe to the origin of life to the origin of everything you can think of. What an amazingly exciting initiative to get started at a university. I'm delighted that Lawrence is talking to us today. Please welcome him.
Thank you. Can you hear me now? Can you hear me now? Okay, good. Thanks, Richard. Actually, let me just say that my friendship with Richard has been a unique one in many ways, but one that's caused me every time we're together to think about things slightly differently. I hope mutually, and a true pleasure and honor to be here. Richard asked me to talk about cosmology, and I originally I talked to Liz Cornwall, who was organizing this, and told her what I was going to talk about, and gave her several titles, and she thought they were too depressing, so she said, "Why don't you just make it We're All Fucked?" But I decided not to use that title. I put this quote up here. Well, I like to have quotes from people when I'm being introduced, so people have something to read. But it's kind of useful, I think, because I'm going to talk about our modern picture of cosmology and how it's changed our view of the universe, the past and the future. And in some sense, how that picture is clearly remarkable, and far more remarkable than the fairy tales that are made up in most religious situations. But the key point is mystery. That's one of the things that makes science so special, I think, is that scientists love mysteries. They love not knowing. That's a key part of science. The excitement of learning about the universe. And that, again, is so different than the sterile aspect of religion, where the excitement is apparently knowing everything, although clearly knowing nothing. Now, in any case, so that's one of the reasons I put this quote up here. But I am going to talk to you about a mystery story. So now I live in Phoenix now, and people know what these are. I used to live in Cleveland, and then I had to tell people these were stars. And this is a picture of a globular cluster, and it's a beautiful thing on a nice clear night. But what I want to talk to you about is how our picture has changed the universe so much that the really important stuff in the universe is not the stars and galaxies, but the stuff you can't see, the mysterious stuff that dominates nature. Okay, so it's a mystery story, so let's begin. It was a dark and stormy night. And Einstein had just developed his general theory of relativity in 1916. And an interesting time, because he had developed that theory, which was the first theory of not just how objects move through space, but how space itself could expand and contract and be dynamical. A remarkable theory that told us that space curves in the presence of matter. And it was beautiful, and he kind of knew it was correct. But at the time, it disagreed with observation, which used to bother physicists in the old days. And the observation was that the universe was static and eternal. That was the conventional wisdom in science at the time, that the universe had been around forever and would be around forever. And his theory didn't agree with that, because his theory of general relativity suffered from the same problems that Newtonian gravity suffers from. Gravity sucks. It always pulls. It never pushes. And if you put stars and galaxies out there, they will not just stay there. Gravity will produce a universal attraction that will pull them together. And so he tried to figure out what to do, and he was able to change his theory slightly, consistent with the mathematical symmetries that allowed him to develop it. So I wanted to show you how he did this. So I have his equations, which is a good thing to do at 9:45 in the morning or whatever. But I do have them in a user-friendly fashion here. Okay. This is for the biologist. No, I'm just joking. So it's not completely facetious, because the left-hand side of Einstein's equations tells you about the geometry of the universe, how things are curved in the presence of the source of curvature, which in this case is the energy and momentum of the universe. So that's fine. And in fact, I'm a theoretical physicist, so I have to write the actual stuff, the Greek letters. That's much more illuminating for you, I'm sure. So this was the theory that didn't work, that explained the universe we didn't live in, or so he thought. And so he was able to change it a little bit by adding an extra term to the left-hand side, which he called the cosmological term. This term on the left-hand side would produce a small repulsive force throughout empty space, so small that it wouldn't affect the Newton's laws, which of course describe beautifully, or developed, in fact, to describe the motion of the planets around the sun, and you wouldn't want to destroy that. So small you'd never measure it in the solar system, but it could build up on the scale of galaxies and hold galaxies apart. And so that's how he thought he'd save his theory. Now, shortly after he introduced this term, it became clear that it was a problem. And in fact, here's a postcard I got when I was on leave once in Switzerland, in Zurich, and it's from Einstein to Hermann Weyl, who's a very famous mathematical physicist. And it's in German, and some of your German is better than mine, but this basically says, it's already 1923, and he's already saying, if you get rid of a quasi-static universe, then out with the cosmological constant. Because he realized that if the universe is really expanding, which is what we now know, and I'll talk to you about how we know that, then you don't need a cosmological constant anymore. If the universe is expanding, gravity can be universally attractive. And just slow the expansion, and the big question of 20th century cosmology became, is there enough gravity to stop the expansion? How will the universe end? Will it end with a bang or a whimper? Will it end with a big crunch, the reverse of the Big Bang, or will it expand forever? In fact, and that's the reason why I, as a particle physicist, got involved in cosmology, because I wanted to be the first person to know how the universe would end. It seemed like a good idea. And you'll see where that came from. But anyway, so in 1923, Einstein said, I wish I hadn't put it in, and threw it out, but it was really not 1923, but 1929, when we really knew the universe was expanding. And this is the person who convinced us. This is someone, and I always say this, so some of you may have heard me say this before, but it's true. This guy always gives me faith in humanity. This is Edwin Hubble. And he began life as a lawyer and became an astronomer. And so there is hope. And he made many discoveries, and I think because I'm a little short of time, I won't talk about one of the ones he made, but the biggest one he made, of course, was the discovery that the universe is in fact expanding, and it changed everything. And this is what he discovered. Now, these are not sperm, these are galaxies. These are, again for the biologist, so our galaxy is here, and when we look out, we see what he discovered was that all other galaxies are moving away from us on average. And those that are twice as far away are moving twice as fast. Those that are 3 times as far away are moving 3 times as fast, etc. And so, and we codify this saying velocity is proportional to distance. And now, what does this tell you? Okay. Well, it obviously tells you we are the center of the universe. Okay. And actually it does. And in fact, my wife reminds me of that on a daily basis. And it really means is that the universe is expanding uniformly in all directions. Now, why does this ridiculous observation that where everything's moving away from us tell us that? And I've spent a lot of time trying to think of different ways to explain this, none of which have been particularly satisfactory, but I think the only way to understand it is to get outside the universe. We're in California. It's easy to do that here. But let me do it this way. Here's a universe that's two-dimensional and that you can stand outside of. And here's, I've put the galaxies at nice uniform distances here. And again here, and you can see at a later time the universe is bigger. The galaxies are a little bit further apart. So if you were standing outside of that universe, it would be obvious that it was expanding uniformly in all directions. Now, what would you see if you were on that universe? Well, just pick a galaxy, any galaxy. And the way we can figure out what you'd see from that galaxy is to superimpose this image on top of this one, placing this galaxy on top of itself. Okay, what do you see? You see precisely what Hubble saw. Every galaxy is moving away from this galaxy. Those that are twice as far away have moved twice the distance in the same time. Those that are 3 times as far away have moved 3 times the distance. And it doesn't matter which galaxy you're on. Everywhere you see the same thing. Everywhere you think you're the center of the universe. So, depending upon your mood, either every place is the center of the universe or no place is the center of the universe. It doesn't matter. The universe is expanding. And that really did change everything. And by the way, it had profound religious implications, at least. As some of you may know, that in response to this and other things, the Pope at the time gave an encyclical that science had proved Genesis. And the interesting person, the first person to actually show there had to be a Big Bang, was a Belgian priest who was also a physicist named Georges Lemaitre. And the really interesting thing about Lemaitre is when the Pope said that, Lemaitre wrote him a letter and said, "Stop saying that." Just really amazing for a priest, because he said this is a scientific theory. You can take it if you believe in God and believe in Genesis to validate your beliefs. But you can also take it to mean that, in fact, the laws of physics take us right back to the beginning of time without God. What you take from it depends upon your religious and metaphysical beliefs, but whatever you say, the Big Bang happened. And I think that's if we could just convince a lot of people of just that simple thing, that the universe is the way it is, whether we like it or not, I think we'd overcome a lot of problems in this country, and I have to waste far too much time on that. But anyway, okay, but this is a science talk, although I'll throw in little bits of commentary throughout, I suppose. How do we know the universe is expanding? It's such an important thing. I want to spend a few minutes on that. Well, we do as these two guys on the plane out there near Arizona say to one another, "I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect." Now, what they're pointing out is that when a train comes towards you, the train whistle sounds higher. When a train moves away from you, the train whistle sounds lower. And that same principle was used by Hubble and others. The same is true for light for very different reasons. So when we look at distant galaxies, if they're moving away from us, the light, which is a wave, gets stretched out. The longer wavelength part of light, or the red end of the spectrum, so it's called redshifted. And galaxies are more and more redshifted the further and further they are away from us. So that's how we know their velocity. The velocity is easy. How do you know distance? That's really hard. The universe is a big place. And we don't have tape measures that are that big. We have to find a way of determining distance without actually going to a place, and that's hard. And in fact, one of the ways, well, of course, the way we do it is we use physics. We could determine the distance to the back of the room if I turned out all the lights and only one light was on, and I knew it had a 100-watt light bulb, by having an old-fashioned camera, which none of us have anymore, that had light meter on it. And if there were 100 watts there and I was receiving 1 watt of light here, I know how that light spreads out as 1 over the square of distance. And so I could determine by how much wattage I was receiving here, knowing the wattage of that light bulb, how far away it was. Okay? The undergraduate or high school physics exercise. The problem is the universe isn't full of 100-watt light bulbs. If it was, life would be easier. So we have to try and find the equivalent. We have to try and find what's called a standard candle. Something whose intrinsic brightness we understand, and therefore when we look at it through a telescope, we see how bright it appears through the telescope, and we work backwards to figure out how far it is. That's the hard part. That's why it's been so hard to determine the rate of expansion of the universe, because it's hard to find standard candles. This is Hubble's original data from 1929. And this is one of the reasons he was such a great scientist, because he knew to draw a straight line through this data set, which itself is already not so clear. It's not obviously the right answer. But what he found was, in fact, that velocity is proportional to distance. Okay? And the great thing is he got the answer wrong by a factor of 10. which was an embarrassment at the time. Again, I'll throw a little commentary in it. Because if the universe were expanding this fast, you could calculate its age, and its age would be 1.5 billion years old. That was in 1929. Now, as anyone knows, if you read any of Richard's books, you would know that, well, by 1929, we already knew the Earth was older than 1.5 billion years old. And so it was embarrassing that the universe was younger than the Earth. One of the many embarrassments in cosmology that's happened over the years. And in fact, taken by some people to once again argue that science didn't know what it was doing. But the problem was, of course, he wasn't a bad astronomer or a bad scientist. The problem was trying to measure distance because he didn't have good standard candles. And that's, as I say, been the holy grail, if you wish, of cosmology over the last century. And we now have standard candles. Here's one. I wish there was better resolution on this projector. It's a beautiful picture from the Hubble Space Telescope of a distant galaxy far, far away and long, long ago. And there's a whole galaxy. It's about 1 billion light years away. We're looking at it as it looked 1 billion years ago. So many of those stars no longer exist. And here's an object that's just as bright as the whole center of the galaxy. You'd think it's a star that's near in our galaxy that just got caught in the picture frame. It's not. It's a star on the edge of that galaxy that has exploded. And exploding stars shine with a brightness of 10 billion stars. They're the brightest fireworks in the universe, supernovae. And they're remarkable, and I keep having asides. Maybe I'll get to my point eventually. But this is something that I wrote a whole book about, and someone asked me yesterday why I wrote that book. Because it is the most poetic thing I know about the universe. Richard wrote a great book called, what's it called? Our Ancestors? What's it called? Ancestor's Tale, yes. I wanted to make sure I got that right. And I wrote a book that was a different Ancestor's Tale. It was called Adam. But the amazing thing is that every atom in your body came from a star that exploded. And the atoms in your left hand probably came from a different star than your right hand. It really is the most poetic thing I know about physics. You are all stardust. You couldn't be here if stars hadn't exploded because the elements, the carbon, nitrogen, oxygen, iron, all the things that matter for evolution weren't created at the beginning of time. They're created in the nuclear furnaces of stars, and the only way they can get into your body is if the stars were kind enough to explode. So forget Jesus. The stars died so that you could be here today. Okay? And anyway, this is great. Anyway, so the point is, the real point of the reason I showed this picture is that these objects, these exploding stars, are great standard candles. We can actually observe them amazingly, even though only one occurs every 100 years per galaxy. There are enough galaxies that if you put your hand up in the night away from LA and looked in a dark spot in the sky and made a hole the size of a dime, with a large enough telescope you could see 100,000 galaxies. And that means that even though stars explode once every 100 years per galaxy, in that little region with 100,000 galaxies, on a given night you'll see 10 stars explode. The universe is huge and old, and rare things happen all the time, including life. And so it's an amazing thing. And we can observe stars exploding, we can measure their brightness, we can measure their colors, and that has allowed us to produce a great standard candle. And after 75 years, we now can determine the expansion rate of the universe. This is a new Hubble diagram, much better than Hubble's. It was made after the discovery that on a log plot everything is a straight line. But even still, we now know the rate of expansion of the universe to 10%, not a factor of 10. And we therefore, in fact, we now know the age of the universe through other things extremely accurately to almost 4 decimal places. 13.72 billion years is the age of the universe. It's amazing that we can say that with a straight face and have scientific reasons to support that. Okay, great. So let's go back to Einstein. Einstein had this cosmological term. He said, "I was my biggest blunder. I want to throw it out, get rid of it." But the problem is you can't get rid of it so easily. Because using the miracle of modern mathematics, you can rewrite that equation. And now this is a small step for a mathematician, but a giant leap for a physicist. Not because it's that hard to put this term over there. Most of us could do that. But because it now represents something very different when it's on this side of the equation. Here it was somehow a geometric quantity. When it's here, it looks like a new contribution of the energy and momentum of the universe. What could contribute a term like this? And we know the answer. Nothing. By nothing, I don't mean nothing, I mean nothing. If you take empty space, and that means get rid of all the particles, all the radiation, absolutely everything, So there's nothing there. If that nothing weighs something, then it contributes a term like this. Now, that sounds ridiculous. Why should nothing weigh something? Nothing is nothing. The answer is nothing isn't nothing anymore in physics. Because of the laws of quantum mechanics and special relativity, on extremely small scales, nothing is really a boiling, bubbling brew of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Now again, that sounds like philosophy, like counting the number of angels on the head of a pin, or religion, or something useless. I shouldn't say, Dan Dennett is here, I shouldn't say philosophy is useless. But anyway, he's also a friend. But the point is, we can't measure virtual particles directly, but we can measure their effects indirectly. And in fact, they're responsible for the best predictions in physics. Here, by the way, is actually an animation that was shown at the Nobel Prize ceremonies about 5 years ago by a friend of mine who happened to win the Nobel Prize for developing the theory that produced this. This is the space inside of a proton, the empty space inside of a proton. Not where the quarks are, but the empty space between the quarks. And this is an animation, but it's an exact animation coming from physical calculations. This is what the space looks like. Now, how do we know that? Well, there are a lot of reasons, but one of the things are, it turns out most of the mass of the proton comes not from the quarks within a proton, but from the empty space between the quarks. These fields popping in and out of existence produce about 90% of the mass of a proton. And since protons and neutrons are the dominant stuff in your body, the empty space is responsible for 90% of your mass. So these empty space is vital to science, and these calculations are vital to understanding not just protons, but electrons and atoms, and produce the best comparisons, and I will repeat this, the best comparisons between theory and experiment in all of science. To 10 decimal places in quantum electrodynamics, using these calculations, we can get the right answer. It's amazing. So, if that's the case, let's calculate the energy of nothing where there's nothing else. And when we do that, we come up with a calculation which is pretty bad. It's the worst prediction in all of physics. We calculate, you can't even see it, I think, there's a 1 at the end of that. We calculate that the energy of empty space is a gazillion times the energy of everything we see. That, as I say, is the worst prediction in all of physics, which is why we didn't talk about it for a long time. We calculate that empty space should have an energy of 120 orders of magnitude more than galaxies and stars and people and aliens and all the rest. And if that were the case, we just wouldn't be here. So we knew something was wrong with this calculation. It's been around since I was a graduate student. And we knew what the answer was. Theorists always know the answer. They're sometimes right. We knew the answer was 0, because it's the only sensible answer. Because, you can't cancel a big number like this. Let's say the energy of empty space was comparable to the energy of everything we see. Well, we'd have to cancel this big number to 120 decimal places and leave a finite answer in the 121st decimal place. No one knows how to do that in science. But 0 is a number we can get beautifully in science. We use mathematical symmetries. Things cancel, equal and opposite things cancel all the time in science because of symmetries of nature. So we knew the answer. We didn't know what the symmetry was, but we knew the answer was 0. And we could go to bed at night and that was fine. But the neat thing about cosmology is it's really a science. And science is empirical. Knowing the answer means nothing. Testing your knowledge means everything. And so the question is, we should test what the energy of empty space is. And how could we do that? Well, we weigh the universe. How do we do that? We stand on the shoulders of giants. This is a picture I took in an island off Sweden, which used to be an island off Denmark now, which used to be an island off Sweden. The island of Ven, I think I said that right. And this guy, if you look carefully, he doesn't have the end of his nose. His name is Tycho Brahe. And he, as many of you know, laid the basis for Newton's law of gravity by doing nothing other than spending 20 years on his back, a noble tradition, in this case, looking up at the sky without a telescope, measuring the positions of the planets around the sun. And then he was a crummy feudal lord. He got kicked off that island. He gave the data, went to Prague, gave the data to a hapless assistant named Johannes Kepler, who again spent 20 years without a Macintosh trying to interpret the data, and fudged it, we now know, and came up with, of course, Kepler's laws, which led to Newtonian gravity. And the point is, we can use gravity to weigh the universe, including the weight of empty space. Now, why do we care? The reason I got into cosmology.